Alright, so what we want to look at now is we want to look again at an inclined plane, and we're going to put our block on an inclined plane. Our inclined plane has some angle theta, except this time in this problem, I should say, we're going to include friction working against us on the inclined plane. So whenever we have an inclined plane problem, we always want to set up a rotated axis so that the x-axis is parallel to the incline, the y-axis is perpendicular. Gravity is going to still act straight down, so we have our gravity working straight down, and we can draw a triangle here, and that angle theta here is going to be the same angle theta there by the law of similar triangles. So then the piece that's parallel here to the plane, this is g sine theta, and this piece here, which is perpendicular to the plane, is g cosine theta. So we can break gravity into its components in our new x and y reference frame. So what we need to think about is what's now going on. So we have g cosine theta, g sine theta. And what we want to do is we want to sum our forces in the x and in the y. So when we look at the sum of the forces in the y, this is equal to MAY. And the sum of our forces in the y, we have a normal force that acts up to hold the block on the plane, and we have g cosine theta working against it. So we have the normal minus mg cosine theta is equal to MAY. Now we know that AY is going to be 0 because our system is not accelerating perpendicular to the plane. So that tells us that the normal minus mg cosine theta is equal to 0. When we solve then, we can see that the normal is equal to mg cosine theta. So what happens when we're in the x? Well, in the x, when we sum the forces in the x, that's going to be equal to MAX. So we have g cosine theta pulling it down. So when we look at our forces in the x, we have mg cosine theta. I apologize. Sine theta, this is cosine. We have mg cosine theta pulling it down, and we have a frictional force, the force of friction, holding it back. So we're going to put in minus the force of friction equals sum MAX. So before we look at anything, what we can see is that the frictional force is competing with this force. And if this mg sine theta isn't larger than the frictional force, then our block will remain stationary. And how did we define the frictional force before? The frictional force, we defined it before as mu times the normal. And we know our normal force is mg cosine theta. So this is just mu times mg cosine theta. So frictional force is mu mg cosine theta. So if mg sine theta isn't larger than this value here for the frictional force, our block will just sit stationary on the plane. But as soon as this force, mg sine theta, is larger than the frictional force, we'll have some net force here, and that will cause our block to slowly accelerate down the plane. So it'll start, the acceleration will occur, the velocity will change, and the block will slowly start to move down the plane, gaining speed as it goes. So let's take a look at our acceleration here. So this is mg sine theta minus mu mg cosine theta. And that has to equal MAX. So the first thing we can do is divide out our m, and we see that g sine theta minus mu g cosine theta equals ax. We can also factor out a g, and what we see is that ax is equal to g sine theta minus the coefficient of friction times cosine theta. So what we can really see is that if the sine of theta is larger than mu times cosine theta, then our block will have an acceleration down the plane. If this is smaller than this, the block will remain stationary because, as we've talked about before, the frictional force will increase to match any force against it, but the frictional force will only increase up to a value of mu mg cosine theta. If it's larger than this number, then the net force will be larger and you'll get the acceleration. If mg sine theta is smaller than the frictional force, then the block will remain stationary. So this is kind of how we analyze blocks with friction, or items with friction. We use block because it's a generic item, but when we're looking at things on inclined planes with friction, we always make sure we rotate our reference frame. We take gravity to be straight down. We break it into the components using the law of similar triangles, as we did over here. We look at the summing of the forces in the y. We had two forces, the normal force, which is perpendicular to the block, and we have mg cosine theta pulling it down due to gravity, and that's m equal to the may. We said ay was 0, so then the normal force is mg cosine theta. When we looked at the forces in the x, we had mg sine theta, which is gravity wanting to accelerate it down the plane, but it's being opposed by this force of friction, Ff, which is always opposing your motion. So we had mg sine theta minus mu mg cosine theta, because we always define the frictional force as mu times the normal, and we found the normal by solving the y, and that was mu mg cos theta. So as I've said a minute ago, if mg sine theta is larger than mu mg cosine theta, the block will experience an acceleration. If it isn't, the block will remain stationary. So then we just went through and solved for ax, and the acceleration parallel to the plane is g times the sine theta minus mu cosine theta. And that would cause the block to have an acceleration.